Okay, well, welcome again, everyone. We're now in week 5, so the end is in sight. So this is the last of the renewable energy technologies that we're going to be looking at in this course, because I will finish up with some lectures on storage and system integration. So we're going to look at solar energy, and this first lecture is more about the solar resource than it is about the technology. Then lecture 8, which I'll probably start on today, is getting into the technology. So we're going to look at solar energy, and I'm getting my laser pointer out, and we're going to concentrate on solar photovoltaics. Okay, there's 2 main areas of solar energy that are important. One is solar photovoltaics, and the other is solar thermal, where we use the sun's energy to heat, either for space heating, that is keeping people warm in wintertime, or for generating steam to produce electricity from turbines. I'm not quite sure what the situation in Russia is, but in Canada, the use of solar thermal technologies is very much in its infancy. There is one system that was set up in Alberta about 5 years ago, which has subsequently been shut down. On the other hand, southern Alberta, which is about the same latitude as Novosibirsk, Calgary is 51 degrees, Novosibirsk is 54 degrees. The solar energy resource in southern Alberta is just about the best there is in Canada. I'm not sure what it's like for you people. Maybe someone can look for some solar data for Novosibirsk region and tell me what the answer is. But southern Alberta is actually a very sunny place, and sunshine combined with low temperatures is a perfect mixture for solar photovoltaics, because the efficiency of producing electricity from the photovoltaic systems that you see here actually improves as the ambient temperature goes down. And that's one of the features of solar photovoltaics that we'll be looking at. So the concentration is on electricity generation through photovoltaics. And we're going to start off by just stating some fairly obvious facts about the solar resource, and most of you will know most of this sort of stuff anyway. Okay, so we're relying on the incident radiation on the Earth's surface to generate electricity, and this is a diagram or a graph that shows the. Okay, so what we're looking at here is a distribution of the radiant energy as a function of wavelength. And we're looking at the visible spectrum, that's the ones that you and I can see, and moving somewhat into the infrared region, which is a region where some photovoltaic technologies can extract the energy. And the approximate relationship for this energy distribution is one that you probably already know. And if we integrate that to get the equation for the total emissive power of a black body, which is a good approximation for the sun, we get the famous Stefan-Boltzmann equation. Those are obviously fairly basic calculations or formula for the distribution of radiation. In practice, it's not quite a black body radiation. And what you see here is actually 3 graphs of the spectral distribution of the radiation. The dotted line or the dashed line is what it would be if it was a perfect black body at the sun's effective temperature. The black solid line at the higher of the black solid lines is the radiation that is seen just outside the Earth's atmosphere. And there's a thing called the solar constant, which is a typical value of the incident radiation at the edge of the atmosphere. And the number is about 1360 watts per square metre. To get to the Earth's surface, of course, the light has to travel through the Earth's atmosphere, and it gets dispersed by the atoms and the molecules that are in the air. And so by the time it gets to the surface at around about sea level, we're down to typically 1 kilowatt per square metre. And that's a useful number to remember. It's a simple number, and it can be used to give some pretty good indications of what a system is capable of. So particularly, for example, if you know what the capacity factor for a photovoltaic system is, then knowing that the maximum radiation is 1 kilowatt per square metre, you can do some fairly quick and sometimes surprisingly accurate estimations for the power production from a system. So we lose something like 40% of the radiation in getting from the edge of the atmosphere to the ground, which means, for example, that photovoltaics typically works better at higher altitudes where there is less interference from the constituents of the atmosphere. Okay, just a few terms or names, possibly because you may not be able to understand me saying it in my Australian accent. So if we have radiation hitting a surface, then there's basically only three things that can happen to it. It can get absorbed, it can get reflected, or it gets transmitted. And clearly, at some point, we're interested in what gets absorbed, because that is obviously how the energy gets to the photovoltaic module. Or if we were heating up a working fluid to make steam, that energy would have to be absorbed by the working fluid. Reflected or transmitted is important. For example, we don't want any of the radiation that reaches a solar module to be reflected, and we certainly don't want it to be transmitted. Transmission is usually not a problem for photovoltaic systems, but there are some issues to do with reflection, partly due to the fact that all commercial photovoltaic modules have a glass cover on them. And that glass cover is basically for protection, protection from things like hail damage, and it has an effect on the amount of energy that actually reaches the surface of the photovoltaic module. Okay, so obviously absorptivity is usually maximised by having a black surface. A couple of important definitions are beam radiation. And beam radiation is the radiation from the sun that comes directly to the surface. So if you are brave enough to look at the sun, then what hits the retina of your eyeballs is the beam radiation from the sun. Sometimes it's called direct radiation. The alternative is diffuse radiation, and that is radiation that can be scattered from clouds. The distinction is important because some photovoltaics, and I'm going to be using the symbol PV for photovoltaics. So anywhere you see the symbol PV, just mentally insert photovoltaics. And quite a number of PV technologies do not respond to diffuse radiation. Typically, diffuse radiation can be around about 10% of the direct radiation. Sometimes I've heard that I mentioned before a maximum ground level radiation of 1 kilowatt per square metre. I have been told that in desert climates, it's possible to get instantaneous surface radiations significantly greater than 1 kilowatt per square metre. And the reason for that is the radiation that has been scattered by clouds in the atmosphere. And it can only happen instantaneously. It can't be maintained for any length of time. The rate at which the energy falls to the surface is sometimes given the name irradiance or irradiation, or sometimes called insolation. And the solation part of the name comes from the same root word as solar, for solar energy. And I will probably use those terms interchangeably. So we're looking at how much energy per unit area is coming from the sun with those quantities. And you probably can appreciate that any surface that is black is going to have a high absorptivity and also a high emissivity. So obviously a black body is the perfect radiator, and it would have an emissivity of 1. Okay, just a few facts about the sun and the Earth's part around the sun. It's crucially important that the axis of rotation of the Earth is at an angle, 23.45 degrees to the normal, and that inclination is what gives us the seasons. And clearly, they have a significant effect on the weather. We've got snow on the ground in Calgary now as well. We expect summertime to be much warmer and drier, and probably the same holds for Novosibirsk as well. In addition, we need to define a number of terms related to the position of the sun. Alpha is the altitude of the angle, which is the angle that the sun makes to the origin here. Delta is the value of that at solar noon each day, and solar noon is a point in the day where if we ignore clouds and other issues, where the irradiance would be the maximum. And that value, the declination, is important for sizing and also for orienting photovoltaic systems. And the final one is the azimuth angle. And we'll see, we've already seen it when we've used SAM very briefly before, but I'll show it to you again. Azimuth and tilt angle, which is related to the altitude angle, are very important factors in determining the performance of a photovoltaic system. Okay, again, just some information that you're probably well aware of. I'm not exactly sure where this data is from. It's from somewhere in the north of the US, so probably not quite as extreme in its difference between midwinter, where we are now, and midsummer, where we'll be in June. But in terms of altitude and azimuth, obviously there are huge changes in those angles as we go through the year. And the significance of that is that all solar systems have seasonal variation in their output. Okay, it's clear, I think, already that when you have a climate with something like 16 plus hours of sunlight or daylight during the summer and less than 8 hours during the wintertime, as well as these angle differences, that it is very hard to get the comparable amount of solar energy out of a system in winter as in summer. There are ways that we can redress that imbalance, and I'll show you some of those later on, but you can't obviously change the basic facts of life that are indicated by this diagram here. Okay, this is a small photovoltaic system that is actually established at the University of Calgary campus. This isn't the university campus here. This building was actually built by a group of students for a competition in the United States, where they had to design and build a sustainable house with photovoltaics on the roof to provide the energy. And the reason that I show this slide is the first piece of information you need to know is that all these modules are facing south. Okay, so in terms of the what am I trying to say? In terms of the inclination, they are going to be in the best possible place. In addition to facing south, you can see that there is a change in the tilt of the PV modules, and that's what we call azimuth. And in addition to that, you can just see on top of the roof, there are two modules that are laid flat on the roof. So these modules have no inclination and they have no azimuth. Now, we're going to see that the optimum value for inclination is about 10 degrees less than the latitude. So for Calgary and Novosibirsk, the best inclination angle is somewhere about 40 degrees, which is what these modules are. Down the bottom, you can see the output of the data monitoring system for this photovoltaic system. It's every time you buy the power electronics for a PV system, the providers of the power electronics allow you to broadcast the system performance to the internet. And that is a very simple way of monitoring the performance of the system. And we're going, as we go through this section on photovoltaics, I'm going to use some examples of internet-based monitoring to show you things about the performance of the system. So, for example, this shows about a week's worth of performance in March. So, by Calgary standards, that's towards the end of winter. And you can see the number of kilowatt hours that have been produced from each of the modules during that time. Now, the actual numbers themselves I don't want to talk about, but what I do want to talk about is how they change with the change in azimuth. So you can see that the modules in the center of the array, these ones here, which have virtually no azimuth angle, produce significantly more than the modules at either end of the array, which are considerably inclined in the east-west direction. Okay, so here, for example, we go from about 3 kilowatt hours so far up to about 3.16. Not a huge difference, but that's because we're not in the high solar energy season. If I had used data from June, then this difference would be much more significant than you see here. And the other thing I would like you to note is how poorly the modules that are laid flat are doing. These are actually the worst performing modules in the whole array. And as I pointed out before, they have no inclination and they have no azimuth. Okay, so one of the things that we're going to be looking at in this section of the course is concentrating on photovoltaic systems that don't have any tracking. You know, there's no mechanical device here to allow the modules to follow the direction of the sun. And that's very common, particularly on building mounted systems, because if you're going to have tracking on a building mounted system, that means that you have to move the modules well above the roof, and that can give you extra problems with additional wind loads on the structure and difficulties in getting approval for it. So virtually all the systems that we're going to be talking about in this course are fixed modules. And so the choice that we have is usually what inclination and what azimuth angle we're going to use. And I've just realized that I have turned my video off. So maybe I'll just stop sharing for a moment and turn it back on, because I didn't mean to do that, and start screen sharing again and go to the next slide. So what you should see now is the same system for much the same time of the year, and this is showing the instantaneous energy production. So at this particular time, these modules here are producing over 100 watts these modules are producing 50 watts. And I'd like you to note particularly the modules on the extreme right of the array here. See how little power they are producing? Anyone like to guess a reason why these two modules are not producing much power? And I'll tell you before you think about it, there's nothing wrong with these modules. These modules don't have any faults.
Something with snow.
You're very close, Stephen. It's actually shading. Okay. You can see, if you look down the bottom here, you can see little graphs that show the production over the days. So there's 1, 2, 3, 4, 5, 6 days here. And you can see the cursor that is showing this data above here is in early morning. And you can't see it from the photo that I showed you before, but outside the installation of this building on the university campus is a street lamp, a lamp that provides lighting for cars that are parked in the car park there. And in early morning, that street lamp shades these 3 modules. Okay. And so instead of producing even, say, 55 watts that the ones on the other side are producing, it's down around 18 watts. And that's an indication of how important avoiding shading is for solar photovoltaics. And I'm going to be spending at least one lecture talking about how shading affects the performance of photovoltaic systems to show you how significant it is. Typically, shading effects are strongly nonlinear. If you shade a proportion or a percentage of a PV system, then the reduction in power output will be much greater than the percentage that is shaded. And hopefully I'll explain to you in a lecture or two's time why that is the case and how you can calculate it. It's not actually an easy thing to calculate. Okay, we have another photovoltaic system on the university campus. This is on the engineering building. This is a bigger system of about 60 kilowatts. And here I've just got a snapshot again in the morning in March of the cumulative performance of that system. And in addition, this system is a big enough system to have what are called string inverters. In other words, groups of the modules are connected to a single inverter, and you can see the performance of the 2 inverters up the top here. The other system that I was just looking at, this is an example of a system that has microinverters. In other words, each pair of these modules has its own or their own inverter. And I'm going to be talking a little bit about the differences between string inverters and microinverters, what's the advantage and disadvantages of them. And also what I think you can appreciate for seeing these 2 figures is how much data can be made available from photovoltaic systems. It's an extraordinary amount of data. And this factors in to an issue of system integration that I will be talking more about at the end of the course. Now, imagine you live in a place where there are a lot of rooftop solar PV systems. For example, in California, there's over 1 million rooftop photovoltaic systems. And in the state of Western Australia, rooftop PV is the largest generator on their electricity grid. Okay, so there are situations where systems like this, and this is a relatively large one, are producing a significant amount of power for the electricity system. Now, think about some of the consequences of that. If you own a wind farm or a solar farm that is producing megawatts of power, then you have to report your power production to the electricity system operator. The system operator needs to know how much power is coming out of each wind farm and each solar farm, so they can do that very delicate balancing of production of electricity versus the consumption of it for the whole grid. Now, if you have 1 million rooftop solar photovoltaic systems, those systems do not have to report their power production. Okay. In California, those 1 million solar photovoltaic systems are feeding electricity into the grid, but they're not telling anyone how much they're producing. Okay, that can be a huge problem for the system operator, because the system operator has to either estimate the power production or they have to do something else to deal with the problem. And estimating the power production is an obvious thing to do. Now, this situation of both having a large number of distributed PV systems and the ability to broadcast the performance of those systems, that's a relatively recent phenomenon. And it's only about 10 years ago that something like this was actually achievable, that you could actually broadcast the performance of these systems to the web. So I work with a colleague in the electrical engineering department in Calgary, and he is interested in all these issues of system integration and whatever. And we were discussing the problem of, if you do have a lot of distributed PV, how do you estimate how much is going into the grid? And we had the idea, what we should do is data mine these websites that are actually storing the production from all these private systems. So we hired a very competent programmer over summer, and we got the programmer to work with a PhD student, and they data mined about 70,000 photovoltaic systems in California. And they downloaded as much data as they could from the website before they were caught, because the company that provides the web service is actually the company that produces the inverters. And they saw that we were doing this huge data mining activity, and they realized what we were doing, and they shut us down. And so we got about 1.5 years worth of data before the company shut us down. But that was still enough data to construct probabilistic models for the electricity production that we distributed around the state of California. And we could actually accurately estimate the gross production of distributed solar energy that way. So it's just a nice little story. And people have followed up that idea and have done subsequent work on. But it's a nice little story that just shows you that one of the basic problems that you can get with distributed energy production can actually be overcome with modern technology and the ability to broadcast the performance of the system. Okay, back to a few definitions. There's an important quantity, the ratio of beam radiation on a tilted surface to that on a horizontal surface at solar noon, because this is starting to address the issue of the tilt angle, beta, or the inclination angle, as it's sometimes called. Okay, so if we're going to stick with fixed photovoltaic installations, the only choices that we have in those installations is the angle beta and the azimuth angle. And so this equation gives us the ratio of the beam radiation. And so that gives us, in effect, the value of actually sloping the modules at that particular angle. And where it becomes important is when you are in cities like Calgary and Novosibirsk that are at high latitudes. If you're at the equator, then the best inclination angle is 0 and the best azimuth angle is 0, and there's no fun. There's no excitement or no professional judgment involved in how you install your PV modules. However, the higher your latitude or the closer you are to the North Pole, the more important the inclination angle becomes. And what you see from studies of production over a year is that, again, remember, these are not tracking systems. These are fixed systems, that if you have your tilt angle at something like the latitude minus 10 or 15 degrees, you produce more power in summer. And if you think about the additional fact that you get many more hours of sunlight during summer, if your aim is to maximize the annual energy production of your system, then that is the appropriate inclination for your module. It's not particularly sensitive to this number here. As we'll see when we do some SAM calculations of capacity factor and annual energy production, whether it's 15 degrees or 10 degrees doesn't particularly matter. It's a very flat maximum. So if my goal as a solar farm owner, or indeed as a person who's installed photovoltaic modules on the roof of my house, and I want to maximize over the year how much energy I produce, then that's what I do. On the other hand, I might want to bias my winter production. Okay, and that's a situation that's appropriate, particularly for solar thermal applications. Okay, because if you have a solar thermal system that is producing hot water for you to have a shower and wash your dishes and wash your clothes and things like that, you want to have the same amount of hot water in summer as you do in wintertime. And in that case, you need to bias your module or your solar system so that it is producing more power in winter, in which case you would go to latitude plus 10 or 15 degrees. In fact, in Calgary, as you can see here, and Novosibirsk will be very little different, the best angle the best inclination angle for wintertime production is about 76 degrees. So it changes significantly from somewhere about 40 degrees up to somewhere about 80 degrees, depending on what outcome you want from your solar system. Okay, obviously, if we could track, then this becomes incorrect, because you're able to do the optimization as you go. So that is the first lecture that I wanted to give you on the solar resource. We've got plenty of time tonight. So I'll start sharing the screen again, and I'll move on to the next lecture, which will take probably today and most of tomorrow. Okay, so can you see the front of that lecture 8?
Yeah.
Okay, so here's let me put my pointer on again. So here is a photo of the system that I was just talking about. This is the version of it in Washington, D.C., where the students went for the competition. This is a version of it that is on the university campus, and you can't see the street lamp that is shading those modules. It's just outside the photo here. Where the laser pointer is east, and where it is now is west. So like I said, this is it's actually the only PV installation that I know of that has a variation in the azimuth angle, which makes it particularly interesting. If you have a look at the system above that, what do you notice about that system? We're going to spend nearly a whole lecture analysing the performance of this system. Okay. Can you see from that photograph why we might be doing that? Have a look in the bottom corner here. If you look carefully, and it might be easier to see on the PowerPoint itself rather than on the screen, this area is shaded. Okay, you can see there must be a tree behind the photographer's head that is actually shading the modules there. The percentage of shading of the whole relative to the whole system is quite small. I forget the actual number now. We'll learn it in a lecture or two's time, and we're going to see that amount of shading has a much greater effect on the power output than the area of the modules that are shaded. So we're moving towards enough of a knowledge of how photovoltaic systems work in order to understand issues like shading, to understand why we have particular inclination angles, why generally speaking we have no azimuth angles on a solar farm. And because I had a little bit of space down here, I thought I would reproduce this cost graph that I had in the first lecture. This is from the first lecture as well, just to show the main costs of a PV system. If you take the labor out, then the most important costs are the modules themselves, which are shown in yellow here, and the power electronics or the inverter that is shown in the blue. And when we get on to look at the power electronics, many of the issues that are important for photovoltaics, we've already met in the context of wind turbines. Okay, PV produces DC power output, but the voltage of that output is changing all the time, depending on the incident radiation and the temperature, and the current that's coming out is also changing. So you have to do power electronics transformations of that sort of fluctuating DC power to produce grid quality power, but you also have to implement maximum power point tracking for PV. The most important variable for the power production is the radiation. And when you have a situation, as we do in virtually every part of the world, where clouds can occur, then whether a cloud is blocking the PV system from the sun or not has a huge impact on its performance. And that effect is multiplied by the fact that photovoltaics has no inherent inertia. So if you switch the sunlight off, you switch off the power that the PV system produces. Okay, and so the fluctuations in power output that you get from PV systems can actually be greater than what we've seen, very substantial fluctuations for wind power systems. Okay, again, some information from lecture 1 that I wanted to repeat because we are getting to the stage where we should be able to understand what the consequences of these are. On the top left, you see a graph of module efficiency for the main PV technologies. Multicrystalline, monocrystalline systems are shown here. And you can see over a 10-year period, typically 2 to 2.5% improvement in efficiency. That might not sound very much, but it is actually significant for 2 reasons. And one is that, as we have also seen from the first lecture, there's been a huge drop in the cost of PV over that time. Okay, so the price of a PV system is coming down and its efficiency is going up. That's a good combination to have. Can anybody else think of what could be some of the consequences of efficiencies for PV systems? It's a pretty obvious one when you think about it, but the efficiency is directly related to the size of your installation for a given power output. Okay, so if you're going to develop a multi-megawatt solar farm with PV technology that has an efficiency of, let's say, 20%, then every square meter of your module at most will produce about 200 watts. So if you want to, then you add in a capacity factor. Okay, capacity factor, same, exactly the same meaning as I've been using it so far. It's the average power output divided by the rated power. For southern Alberta, which is a good solar climate, that capacity factor is less than 20%. So with current technology, a square meter of PV system is producing something like 40 watts. Okay, so how many square meters do you need to produce on average a kilowatt of power output? The numbers are staggeringly high. And one of the issues with photovoltaics is simply the cost of the land that is required to build a solar farm. And particularly if that land is good agricultural land. Okay, because you put a solar farm on land usually means that you can't use it for any other purpose. If it's a wind farm, then you can grow crops or you can graze cattle or sheep around the towers at the wind farm. But a PV or a solar farm is all at ground level. And you stop the land from being used for any other purpose. So that issue, the issue of the amount of land that you need to produce large amounts of intermittent solar power can be a significant one. By the way, it's one of the reasons why there's increasing number of photovoltaic systems on lakes and reservoirs and canals and other waterways, because if you put them on a lake, for example, you don't affect any agricultural land, and you might even reduce the amount of evaporation from the surface of the lake. So they're water-based or waterborne photovoltaic systems are actually becoming quite common. I'm working with some people in Ethiopia, and they're at the University of Bahadar in Ethiopia, which is the main city that is on Lake Tana. And Lake Tana is a big lake in Ethiopia. It actually feeds the Blue Nile that goes all the way to the Mediterranean in Alexandria in Egypt. And that lake has some 20 islands on it. And a lot of those islands have monasteries on them. They have priests or nuns that live on the island. And the islands have a lot of vegetation because this is a subtropical climate. And to install photovoltaics on the island would mean that you would have to cut down a large number of trees. And nobody wants to do that. So we've got a project where we're looking at actually building a PV system to float in the lake next to the island to produce power for the island. Okay, back to the lecture. What I have here is a chart that I showed in the first lecture, which shows the different types of inverters and their costs, which is obviously very important. So the single-phase string inverter is the inverter that is on the bigger of the systems that we have at the University of Calgary. So something like 20 or 30 PV modules could be connected to one inverter. And a string usually means a collection of PV modules that are wired in series together. A microinverter is an inverter that is designed just for an individual module or possibly two modules. And you can see that microinverters are the most expensive. The alternative to a microinverter, where you can do the power optimization or the maximum power point tracking at each module, but have a string inverter, is somewhere between the two in cost. And then you have other inverters that are more appropriate to the large-scale photovoltaic systems. So this is a choice of power electronics that's not available for wind turbines. Okay, and it's not available because each individual wind turbine has to have its own maximum power point tracking. And so you never get a situation, particularly in a wind farm, where the wind regime is identical for multiple turbines. So you can't do maximum power point tracking except for an individual wind turbine. But with PV modules, you can combine either as a string to an inverter or as an individual power optimizer for each module with a string inverter. And we'll be looking at some of those technologies, I think, later in this lecture. Okay, this is a fantastic graph. It's a very famous graph as well. It's called the NREL cell efficiency graph. And if you Google on NREL cell efficiency graph, you'll come straight to this website. What it shows is PV cell efficiency versus year. Okay, now these are almost exclusively research cells. Okay, we're going to see that a photovoltaic module is actually a collection of solar cells. You know, the basic component of a PV module is a solar cell. They're aggregated because the voltage output from each cell is typically less than 1 volt. So it makes sense to aggregate the cells to form a module, which you then put in a PV installation. And what's really interesting about this graph is that it shows the different photovoltaics technologies. I'm going to start with the blue data, okay, because the blue data and the green data are the current PV technologies that are available commercially. Crystalline silicon cells and different types of thin film technologies, they absolutely dominate the commercial PV market at the moment. And if you look over here at the trend lines for the efficiencies of those technologies, you can see that they're probably reached their limits, whatever they are. There are some theoretical limits for PV cell efficiency, sort of a bit like the Betz-Joukowsky limit, but I don't think they're as useful for PV modules as they are for wind turbines. So the conventional technologies obviously have been around for a long time because there's more green and blue over this side of the graph than over this side, relatively speaking, and they've more or less reached their limit. But what they haven't done yet is they are yet to be maximized they have yet to be optimized in terms of their manufacturing costs. Okay, I think it's a very important lesson about energy technology generally. What's happening with wind and solar is that we're basically using technologies that are 20 or 30 years old. Okay, but what has been achieved is the capacity to build those technologies in cheaper and cheaper forms. Okay, and this is partly the intense competition that occurs in the wind industry and the solar industry. It's about improving the manufacturing techniques, but it's actually not a lot about research and development, unfortunately. But what is really exciting about photovoltaics that is not the case for wind turbines is that there is a lot of new technologies that are coming on the scene. So if we look at what are called multi-junction cells, and they're in the purple here, and they're the ones up here, you can see that in the laboratory, they're achieving very impressive efficiencies. We're looking at getting up to close to 50% efficient. And what they do is that they combine different technologies to capture different bands of the solar radiation. I'll explain a little bit about that later on in this lecture. So they're still marching upwards in terms of efficiency. As far as I know, they haven't been translated significantly into commercial photovoltaic systems, but that's possibly going to come. And one of the things that is likely to happen along with that is that if you have more efficient cells that are more expensive, then it makes sense to have tracking, and it makes sense to have concentration. Concentrate the sunlight on one cell because that's an expensive cell that has a high efficiency. So not only are these technologies improving the output of the PV cell, they're actually, if they become commercially viable, they're going to change the nature of the business. So a PV solar farm in 20 years' time may look very different to a solar farm now. The other area that is really exciting is this area here, which is called emerging PV. And it's down here. And you can see in terms of time, we're talking about technologies that are younger than 20 years. Which is pretty impressive, and you can see from the slope of the curves that they're getting significant improvements in performance. The absolute magnitude of their efficiencies is low, but some of these technologies, like dye-sensitized cells, are going to be revolutionary because they will change the way in which solar cells are made. Some of these dye-sensitized cells can actually be laser jet printed. Okay, and they are also capable of being printed on flexible material. Okay, so for example, it'll be possible, and there are already commercial examples of this. You'll be able to buy roof tiles that have incorporated photovoltaics in them. And in a few years' time, you'll be able to buy a backpack. And the top of the backpack, which you can use to go hiking or go up into the mountains, it will have a flexible PV system on the top of the backpack, and you'll be able to charge your cell phone while you're hiking in the mountains. So there's a whole range of niche photovoltaic products that will emerge with the developments here. What will be very interesting to see is how all these trends translate into commercial products of the future. Like I said, I think the typical solar farm in 20 years' time will look very different to what it looks like now, but I might be wrong, because these conventional technologies, the blue and the green technologies here, they may continue to decrease in price more rapidly than the advanced technologies can achieve. So it'll be extremely interesting to see. And I think you can get a sense of why I find this graph absolutely fascinating. And every year that I teach this course, I download the latest version of the graph, because for some of the years I've been teaching this course since about 2010, and you can imagine how much it has changed, or you can see how much it has changed in that time. So you will undoubtedly see major developments in photovoltaics technology in your professional life. Okay, now we get on to the difficult bit, at least for me, because I'm a mechanical engineer and I'm not a physicist. And I don't mind explaining how PV cells work to other mechanical engineers, but I feel very embarrassed trying to tell physicists how PV systems work. So if I get this wrong, I would be happy for you to tell me what I've got wrong. It's a very low-level explanation in any case. But the little that I know about the principles of photovoltaics is all to do with the conduction band in the semiconductor material. And bear in mind that I've prepared these slides for mechanical engineers, so I want to give them a very basic explanation of what's happening. So I start off by just explaining the difference between insulators, conductors, and semiconductors. And of course, most of you probably know that we're going to be concentrating on semiconductors for understanding how photovoltaic systems work. And in a semiconductor, the conduction band is almost but not completely empty. And the way in which a solar cell is made is by taking typically silicon. Silicon is still by far the most common base material that is used for photovoltaic cells, and doping it with sometimes nasty materials like arsenic and antimony to produce either N or P-type semiconductors. And those semiconductors obviously control the direction of the electron flow. And for reasons that I don't thoroughly understand, if you make a junction between an N-type semiconductor and a P-type semiconductor, that junction actually behaves as a diode. And if it behaves as a diode, then you can have a flow of electricity in the right direction. And here is an example of an N-type semiconductor and a P-type semiconductor. And the sum total of all that, which would probably take most of a course of lectures on the physics of photovoltaics, which I'm going to skip over, is that if we connect if we have a NP junction and irradiate that junction with solar radiation, then we get a current formed. And that junction is clearly necessary to produce the electric field. And obviously, when the electrons are energized by the photons comprising the solar radiation, they gain energy, and they gain energy by Einstein's famous equation, which I'm sure you know, and you can do other calculations from that as well, which are not hugely relevant to what we're going to be talking about from here on, because we're more interested in how a PV system actually performs rather than the detailed theory behind it. A little bit of what we did for hydro turbines and wind turbines. We want to know a little bit about how the technology works to understand the processes involved, but we're more interested in what the power curve is, or the equivalent of that for a PV system. Okay, and just to finish off for tonight, talking a little bit about the band gap. And the band gap is the critical component for the performance and the efficiency of a photovoltaic system. I'll probably leave it there. I will leave it there, but I'll just point out what I've pasted down the bottom of this slide here. One of the reasons why silicon is used as the primary material for most types of photovoltaic systems is basically its abundance and its cheapness. And it's just about 10:30 your time, so I will stop sharing my screen at that point and ask if anybody has any questions.
I have a short question about impact of thermal solar energy.
Yes.
You know that it's very frequently used in warm countries. So my question is it significant impact to renewable energy using all this thermal solar?
I think at the moment it's a technology that has restricted applications because it is still significantly cheaper. Is significantly more expensive than other technologies. So the numbers that I have heard for, say, solar thermal electricity production is that it's about 3 times as expensive as photovoltaics. But there are situations where it can be important despite the cost. I know of systems in the Middle East where they have a lot of sunshine, and I know of systems that are a combination of photovoltaics and solar thermal. And the idea is that the photovoltaics produces the power during the daytime, whereas the solar thermal system stores the heat energy during the day and produces power at night. So in a climate where you get a lot of very regular sunshine, so you don't have to worry too much about storage over time scales of days, a combination of solar photovoltaics and solar thermal can be a really good one. But I think that the fact that solar thermal systems can store their energy as heat rather than as electricity is an inherent advantage. Whether there will be enough demand to allow the technology to be produced for ever decreasing costs is a difficult one to figure out. My feeling is that the answer will be no, because deserts tend to be places where people don't live. And so, if you're going to produce a lot of power in deserts, then you have very high transmission costs. You've probably read stories about whether North Africa could be an electricity supplier to Europe. And I know of a project in Australia where they want to build the world's biggest solar farm to send the electricity to Singapore. So things like that probably will happen, but I don't think it'll ever be a huge contributor to renewable energy. Okay, any other questions? Okay, well, we're over time already, so I'll leave it there. And tomorrow we'll come back to the slide on band gaps, and we'll go from there. So thank you.